Dear ladies and dear gentlemen, I would like to welcome you to my presentation on new bearing systems in mechatronic drivetrains. In this presentation, I would like to talk about problems and possible improvements for rolling bearings in E-system. And this is a current development project with many partners here at the University in Schweinfurt. My name is Stefan Sommer, and I hold the chair of Quality and Production Metrology and Bearing Technology here at the University in Schweinfurt. I've been teaching rolling bearing technology since 2009. I am head of the module bearings in the FHWS Master's Program, and I'm the co-founder of the Steinbeis Transfer Center of Rolling Bearing Technology. It is a spin-off of the university here in Schweinfurt. Well, since all the presentations are recordings, you are able to start a discussion with me by chat during my speech here. So please don't hesitate, activate your chat and write me a message. Okay, let me quickly go through my agenda. First, a little bit motivation, and then let's talk about the root causes of problems in E-systems. This is electricity, this is slip, and this is hydrogen. Then talk about solutions to improve the problems. Let's talk about known solutions and talk about solutions that have to be developed in the future. And last but not least, a summary. Well, in which applications are the bearings worst affected? And the answer is in all electric drivetrains, especially in frequency inverter-driven applications. This could be in industry applications with motors and electric inverters, frequency inverters, railways, e-mobility, and wind turbines. And why? Because the electricity does not stay in the cable as it should, and some drivetrains are operating under highly dynamic load, especially windmills. Electricity, what's the problem? Let's talk about known damages to bearings in E-systems. Go with me to this little sketch of this electric motor here. It has a drive end bearing and a non-drive end bearing. Let's go to the drive end bearing first. It shows crystalline grease. It shows micro craters in the raceway. And it shows so-called gray frosting on the balls. It's spotty raceway. But if you go to the non-drive end side, you see a completely destroyed bearing. So this is not chocolate ice cream. This used to be a shiny steel ball, just like this one. So in the non-drive-in side, we had the same problems as in the drive-in side, but much more severe. If we go back in history, we see that our ancestors had the same problems. Here, Wilhelm Juergensmeyer published micro craters, ripple formation here, and welding beads in 1937 in Schweinfurt. This is almost 100 years ago. Or Mr. Kohaut published in 1943 in Würzburg a habilitation thesis on ripple formation. So since the electric machine exists, there are also these problems. Okay, my computer. Here is the next slide. So, in recent times, new problems occurred. It is the common mode voltage from frequency converters caused by the pulse width modulation. And here's an explanation. To control the electric motor or generator, a variable adjustable frequency is required. And this is done by frequency inverters. This is the frequency inverter between the grid and the motor. It has an inverter, an intercircuit, and a transformer. In the inverter, the EGBTs, those are those funny things here, insulated grid bipolar transistors. You may have heard of that. They together perform the pulse width modulation. And these rectangular pulses modulate the sine wave signal by varying their pulse duration. But the output is not a perfect sine signal, but rectangular pulses. Whereas the three sine signals from the three motor phases would sum up to 0, the rectangular pulses don't sum up to 0. There's always a residual electric voltage that is causing an electric current in the system. And it is called the common mode voltage. This common mode voltage is high frequent, and it is causing damages in the bearings or in the entire system. To sum it up, there are three potential causes: EDM bearing currents, electric discharge machining, spark erosion, like we know from tool making. It is a discharge current when exceeding the breakdown voltage of the bearing lubrication film. Here is a little picture of Professor Sink, who is also in this bearing application world. Here is a shaft, the inner ring, the outer ring, and the plastic housing. And in between there are the balls, and at the balls we have a discharge between balls and the inner ring. We put an electric voltage on the shaft, and this is what happened: discharge at the balls. And there is a high frequency circular current through the motor shaft, the bearings, and the housing. Here is a little picture from EGIS. And there is a rotor to earth bearing current. It's also a high frequency current from stator via the bearings over the shaft to the ground. There are authors who recently published on that topics, and it's Mrs. Mütze, Mr. Binder, Mr. Tischmacher, Mr. Furtmann. Please refer to my literature, and there you can check the articles. But what else do we see? We see new damages in motors, generators, and also gearboxes. And there are previously rare seen severe damages after a very, very short period of operation time, sometimes within the first 10% service life of robust and durable systems that should normally last 20 years or longer. And you see here a spalling, and from the spalling, actual cracks running through the complete ring, here a long one, here a shorter one. Or we have completely intact raceways. Raceway is completely okay, but under the raceway, there are wide etching cracks. Or here a wide etching crack starting to the left and to the right of a non-metallic inclusion. So there must be more problems than just electric load. And here are the problems at a glance. It is the mechanical component, it is slip. We talked about electricity. And there is a chemical load, it's hydrogen. Now let me go to slip first. Slip is a quadruple killer. Now why is that the case? Well, let's go to a wind turbine and have this as an example. The wind turbine is running at 100% speed and 100% torque. Suddenly a grid loss happens. Now the wings of the wind turbine has to be pitched out of the wind. That means the wings rotate to turn the wing profile out of the wind. This rapidly reduces the torque and the speed starts to fluctuate a bit. A little bit fluctuating speed, but rapidly decreasing the torque. But the shafts are tormented with a strongly varying torque, here up and down, until the complete wing set is fully turned out of the wind. Finally, there is no torque, but still speed. Now the wind turbine has to be brought to a stop. Brake discs are used for this purpose. And again, this is causing a strong varying torque until the torture for our bearings is over and the windmill is brought to a stop. Especially the high variations in torque produces rapidly reversing load zones, and the result is slip in the bearing rings and the rollers. Now, why is slip a quadruple killer? Slip is wounding the raceway surface. Slip drags the maximum stress from the depth to the raceway of the surface. Slip cuts the lubrication film, producing high friction, and slip cracks oil, producing hydrogen. Here is hydrogen formation during sliding tests from Kohara. And we see this is the time axis, and this is the hydrogen formation axis. And you see, once the slip starts, the hydrogen production starts too. So hydrogen, where does it come from? Only for the sake of completeness, there is a hydrogen formation during steel production and during bearing production. But I would like to focus on hydrogen formation during operation. And it's, like I just said, electricity and slip. Topology and water plays a role too, but let's focus on electricity and slip. Let me go to electricity. Electricity is the pathfinder for hydrogen, and it is a triple killer. So what happens? Electricity cracks the hydrocarbon chains, the oil, and it is randomly cracking this oil, producing hydrogen. Electricity is wounding the surface. We remember this picture from a couple of slides before. Wounding the surface, enabling the hydrogen to penetrate. And electricity kills the lubrication. And on top, it is producing hydrogen. Hydrogen, how does it work? Well, hydrogen goes where there is space, and hydrogen embrittles the metal. My colleagues in Bochum, Professor Pohl and Dr. Mahnke, who are experts in material engineering, have the explanation for wide etching cracks starting on non-metallic inclusions, like we see here in this picture. We remember this picture again, it's the same picture, non-metallic inclusion to the left and to the right, a wide etching crack. So for an explanation, we go over to this metallic structure. A non-metallic inclusion is a disturbance of this metallic grid, just like an external phase here, or an atomic displacement here. At these locations, there is a little bit more room between the metal atoms. And the very small hydrogen atom is able to go there and to stay there. From here, the hydrogen starts its destructive work. Hydrogen embrittles the metal. The already somewhat higher mechanical stress in this area leads to notch stress. The material begins to crack at this point to the left and to the right of the non-metallic inclusion. This is how the crack starts. Now, more and more hydrogen can accumulate in the crack. The devil's circle has begun. More and more embrittlement by hydrogen, more and more notch stress, and more cracking. One more word on the cracks. The cracks are not white etching from the beginning. Here is a baby crack who wants to become a white etching crack in the future. They become white etching during aberration. And why? Because the crack flanks are rubbing on each other, producing a high local heat. The heat is rehardening the flanks of the crack. On top, if there is electricity, the current flow through the material is redirected. We see it in this picture. And this redirected current flow is heating the area too. When etching the crack now with nitrile acid, the harder material on the crack flanks does not color as much as the softer material around. So the white etching cracks are not white etching. That's a little bit a wrong explanation. They don't etch at all. So the surrounding material etches, and due to the hardness of the crack flanks don't etch at all. They stay white. And this brings me to new bearing systems in mechatronic drivetrains. Let's talk about improvements and solutions in E-systems. And this is what we are doing at the university here in Schweinfurt, together with partners from industry and universities. And most of these partners are also taking part at today's bearing application event. Here are known applications. Examples for known solutions are EMC compliant system design, a good grounding, low grounding resistance, shielded cables, shaft brushes, or in general, a good reverse current flow. Farad rings, electrically filters like sinus filters, and of course, insulated bearings, hybrid bearings, or full ceramic bearings are solutions, or burnished rings, gunmetal gray rings are a solution too. Let me start with these 5 here on top. Well, here are EMC compliant design, a good grounding. And Siemens shows us how this works. Here are the AC conductors for the 3 motor phases. And here is the shielded cable. The shield from the cable is connected to an EMC shield clip. And this EMC shield clip is connected to an EMC shield rail. And this is ground over not a yellow-green cable, because yellow-green cables are for protective grounding. What we need here is a high-frequency grounding band, just like this one. And of course, we need a low grounding resistance. That means we have to measure this grounding resistance first, before installing the system. Here is an example for brushes, shaft brushes. It's an example from etches. And the shaft brushes, they work like this. My mouse doesn't follow me, but here we are. Here how it works. It is a ring with very thin hair, carbon hair, collecting the electric currents the high frequency electric currents from the shaft. And if we do that, this bundle of things, this helps to get rid of the harmful electric current. If there is still electric current left, there are two more possibilities. First, Farad rings. Here is an example from Siemens, Mr. Tischmacher from 2017. It is. It's a bundle of two Farad rings close to the inverter, because those Farad rings, they go between the inverter and the motor. Our partner EPA Systems, who is also in this bearing application world, offers a variety of Farad rings. Please also refer to the presentation of Thorsten Penzel from EPA. Or the electrical filters, sinus filters. Like I said, the sine wave is not so nice and harmonic due to the pulse width modulation. But if you use a sine filter, also goes between the inverter and the motor, it gives us a much more harmonic sine signal. So this also helps to get rid of the harmful electric currents. Well, and then, of course, insulated bearings, hybrid bearings. Insulated bearings, like here, is a ISO code from SKF, is steel rings, inner ring, outer ring, steel, brass cage, steel rollers, but the outer ring is insulated. The same here from FHE, Schaeffler. Steel inner and outer ring, brass cage, but the rollers are silicon nitride. Here's a picture from the Steinbeiß Transfer Center. It is a full ceramic bearing with nitride balls and rings made out of zirconium oxide. Burnishing of rings is a good idea too. We see here a picture of inner and outer ring burnished, a brass cage, and blank steel balls. Burnishing is a mixed oxide, and it improves tripology. For example, it helps against slip a while. And it closes, it passivates at a metal surface against the harmful hydrogen. But once the oxide layer is broken through electricity, through slip, the damaging process is just the same as in any standard bearing. So an EMC compliant system is a good grounding are standards in all systems. But except from that, each system must be individually reviewed. Now let's go to solutions and improvements that we have to develop. There are electrical simulation of the system, the impedance of bearings. My idea is to have technical data showing the impedance of a bearing as well as of a dynamic load. Smart bearings and sensors, industrial Internet of Things. And the sensors would enable us to electrically condition monitor the bearings. So these are pretty low-hanging fruits. These are solutions in the market. The hydrogen sensor and the hydrogen traps are no low-hanging fruits. They are much higher. The hydrogen traps is just like a mouse trap, catching the little hydrogen atoms, just like mice in traps, and keep them there so they cannot do any harm. Well, it's future. Now electrically conductive lubricants, new additives for lubricants, or on-site lubricant recycling. Also seals with electrical properties like the brushes, or conductive bearings or sacrificing bearings are ideas. New coatings for bearings, new insulations for bearings, or optimized motor generator design, new inverter technologies, The matrix inverters don't have that common voltage problem. Or couplings that are dumping the vibration, isolating the gearbox from the motor and the generator. High frequency grounding for bearings. Here in the bottom line, new and better production machinery, new and better in-process measurement and measuring technologies, new better machining tools, new and better processes, heat treatment, for example, new and better steels, materials, and new ceramics. So that's the idea for the futures. And here are our partners. Let me quickly say some words. We have, I just mentioned new measuring technology, better measuring technology, T&S office measuring technology, contour measuring machines, together with QPT or OptoServe. Then we have sensors in bearings, like from HCP Sense or from Best Sense. We have new lubrications like from Nanol or Revitec. We have non-destructive testing methods from Roman and from Golub. We have simulation from Maywald Engineering and from CAD-FM. We have the Eurolab, Eurolabor, and the University in Erlangen, hydrogen experts. We have the MCAR Calibration Lab and the Mardinger Industrial Services for bearing services and calibration in measuring technology. We have Roos Kunststofftechnik for cages, plastic cages. We have EACHES, I mentioned EACHES before, with EMC technology, also EPA, EMC technology, I've mentioned them before. We have Martin, who is able to adjust with shims the perfect preload of the bearings. We have Fraunhofer for testing equipment, especially for wind bearings. We have Eolotech, also wind specialists. I'm sure I forgot somebody. And we have precursor ceramics with the new ceramics, and they all have presentations. Please take your time and follow the presentations of these experts. I'm very glad to have them with us. Last but not least, my summary. A worldwide megatrend of decarbonization will result in growing demands of reliable rotation in mechatronic drivetrains. Rolling bearings are a key success factor to reach the goals. Bearings in mechatronic drivetrains suffer from additional mechanical, electrical, and chemical stress, like slip, electric current, and material fatigue due to hydrogen. This results in very early bearing failures and a very short bearing service life. Nowadays, the root causes are known: electrical inverters, slip, hydrogen, embrittlement. Today, there are a number of known solutions to minimize the problems. Some are reasonable in price, others are expensive. In the future, our world needs new bearing systems for mechatronic drivetrains. To reach this, there are multiple ideas and solutions. Some are low-hanging fruits, and others have to be developed. So join us to work on that. Here is some of my literature. You may refer on that and check what I've done there. And so, thank you very much for your attention. Please feel free to ask questions or start a discussion with me per email or YouTube. Visit me on LinkedIn or check out our master program in Wenzlarer Technik. Thank you very much and have fun.